Draw the shear and moment diagrams for the compound beam. So for this beam, we need to recognize that there is a pin connection between point A and C at B. And because there is a pin connection, we'll have to solve this problem in two separate sections. To do that, let's start with our section AB and draw its free body diagram. For AB, we're going to have a beam, and then at B, we're going to have both horizontal and vertical reactions, but horizontal will be 0. And then at A, we have a roller connection. And now to convert our triangular uniform distributed load into point load, we have to multiply 150 with half times this distance, which is 6, and this comes up to be 450 pounds. Okay, now that we have all the forces, we can try to solve for this. So we're gonna take a moment about the point B to find a solution for AY. We're gonna have clockwise AY, and it's 6 feet away, and then we have counterclockwise 450 pounds, and it's 4 feet away from B, all equals to 0. Solve for AY, we get our solution as 300 pounds. Once we have this, we can use this value to find our solution for VY, which is simply summing the forces in y direction. So we're going to have positive 300 pounds, negative 450, positive Py, all equals to 0. And solving for By, we're going to have our solution as 150 pounds. Alright, now that we have all the required forces for the AB section, we can proceed to the BC section. So at BC, we're going to have a By, which we have just found. It's 150 pounds. And then we have our actions at C, so we can have both horizontal and vertical at C plus a moment at C. We know our horizontal at C is going to be 0. Vertical we still need to find, and then we have a point load. This point load is going to be 150 times 0.5 times 3, which is 225. And this load is 1 meters or 1 feet away from C. Okay, now that we have all the required information, we can first of all find our Cy, which is simply summing the forces in y direction. We're going to have negative 150 and negative 225 pounds, and then positive Cy, all equals to 0. And solving for Cy, we're going to have our solution as 375 pounds. Similarly, we can take a moment about the point C to find our solution for moment C at C. So we're going to have moment C, and then we have counterclockwise 225 pounds, and it's 1 feet away from C. And then we have another counterclockwise 150 pounds, and it's 3 feet away, all equals to 0. Solving for moment C, we're going to have a solution as 675 pound-foot. Alright, now we have all the required forces and reactions we needed. Now we can start drawing our diagram, and then we'll proceed with the equations if we need to. I'm going to begin with the shear. So for shear, looking at section AB, we're going to begin at 300 pounds, and then we are going to go down 450 pounds over the course of 6 feet, and it's going to be second order curve. So 300 take away 450 is negative 150. So let's say negative 150 is around about here, and this is 6 feet. So our curve is now second order, and it's going to be concaving upwards. All right, and then after 6 feet, we have our section BC, which runs for 3 feet. Let's say this is our 9 feet mark. Okay, and then in here, we're going to run down another 225 pounds, which will take us to about negative 375. And this is also second order curve, but this time it's going to concave downwards. And here at 375 mark, Seaway going to lift us up to 0, confirming our calculations for load was correct and forces, and also our graph is correct. Now we can find our function for shear, because we want to find out where this intersection is. This is where we're going to have the maximum moment. And while we are doing the equation for shear, we're also going to find the moment right away. Okay, so for this part, or this region, which we're going to name it region 1, we have our load equation as 0 take away 150 divided by 6 take away 0 times x plus a constant. Simplifying it, we can have a solution as 150 divided by 6x plus the constant. And that's 150 divided by 6 becomes 25. So our load equation is now 25x plus the constant. And to find our constant, we know our load is 150 pardon me, our load is negative 150 when x is 0. Therefore, this 25 times x is going to be 0, and that makes our C as negative 150. So overall, our load equation is going to be 25x plus the constant, which is negative 150. Alright, now we can find our shear equation, which is simply the integral of the load. So it's going to be 25x squared divided by 2, take away 150x plus the constant. To find our constant, we know our shear is 300 pounds when x is 0. Therefore, our C is 300. So we're going to switch our constant from ladder to 300. And now our moment, same idea, another integral. So we're going to have 25 cubed divided by 6, take away 150x divided by 2 plus 300x, and then a constant. This will become 75x squared. Alright, now to find our moment, we know our x is, when our x is 0, our moment is 0, therefore our constant is 0. Rewriting it to make it look cleaner, we're going to have 25 times x cubed divided by 6, take away 75x squared plus 300x as our solution. And now to find our intersect, I'm going to erase this. So we want to know when shear is 0, what is the value of the x. So for that, we have to solve this quadratic equation. And value for x comes up to be 2.536 feet. This means this is where we have the x intersection. And now we can use this value into our moment equation to find our maximum moment. It's going to be 25 times 2.536 cubed divided by 6. Take away 75 times 2.536 square plus 300 times 25.36. Solving this, we get our solution as 346.41 as the maximum. Alright, so now that we have that, we can proceed to our moment equation or the moment diagram. So our moment is going to begin at 0, and then at this intersection point, we're going to go all the way to 346.41 mark, and this curve is going to be third order because third is in line after the second, and this curve is going to be concaving downwards. Then comes our this area. The easiest way would be to just plug in the value into our moment equation. So we're going to do that. So we will have 25 times 6 cubed divided by 6. Take away 75 times 6 square plus 300 times 6 gives us 0. So that means our moment will be 0 at that mark. And our curve is going to be third order. And it's going to be concaving downward. And then comes the next part. Again, it would be easiest option would be to use the moment equation to solve for it. There is a graphical method available as well to solve it. However, it can be a little complex. So my recommendation is always to use the equation, but we will do the same problem with the graphical method as well. But let's first do it with the equation so that we have a mark that can verify our graphical equations or solutions. Okay, so for region 2, we're going to have our load equation first of all. And it's going to be 150 take away 0 divided by 9 take away 6, it's 3x. And then remember, don't forget the constant for the load. This is going to be 50. And now we know our load is 0 when x is 6. Therefore, our c, or the constant in this case, is going to be positive 300. Now we can use this equation to find our shear. It's going to be negative 50x squared divided by 2 plus 300x plus the constant. And for the constant, we know our shear is going to be negative 375 pounds when x is 9. plus the constant. And solve for C, we get our solution as 1050, and it's negative. Okay, and now the moment equation. So for the moment equation, we're just taking another integral. So it's going to be 50x cubed divided by 6 plus 300 x squared divided by 2, which comes up to be 150. And then we have 1050x plus the constant. Alright, now that we have the moment equation, we can determine what our moment is at 9. But before we do that, I forgot we need to find our constant. So let's figure that out real quick. So we know our moment is going to be 0 when x is 6. And solving for our constant, we're going to get our solution as 2700. Now we can plug the value of 9 to find our solution for our moment. So it's going to be 50 times 9 cubed divided by 6 plus 150 times 9 squared negative 1050 times 9 plus 2700. And our solution comes up to be negative 675. So we're going to take our moment curve all the way to 675 and 9 feet mark. And this curve is going to be 12 and concaving downward. And then at 65, there's a moment at C, which is also 675, will take us to 0. Anyways, we could have just used this value of moment C to determine, but I just wanted to show you that there are more than